Hello everyone, welcome to my class. Today I am going to cover divergence theorem, which is also called the Gauss's theorem. First, let me review the flux. The flux of vector field F across the surface S is also denoted by the surface integral of vector field F over the surface S, and which is defined as the Dahal integrals over D, where D is a projection of S on xy plane, and the integrand function is negative p times gx minus q times gy plus r times dA. Now let's put a restriction on the surface. So ask questions to ourselves: what if the surface S is a simple closed surface, like a sphere, ellipsoid, a cube, etc.? Then we have the divergence theorem. So let me state the divergence theorem. If S is a simple closed surface enclosing a solid region E with positive orientations, and if capital F is a vector field with component PQR, then the flux equals to the triple integrals of divergence of vector field F over E and with respect to volume element dB, which is also same as the triple integrals over E of Px plus Qy plus Rg times dV. Here dV is a volume element. In rectangular coordinate systems, dV is dg, dy, dx. In cylindrical coordinate system, dV equals to r dz dr d theta, and in spherical coordinate systems, dV equals to rho square sine phi d rho d phi d theta. Great. So now let me make a 2 point here. Point number 1, the divergence theorem converts the double integrals into a triple integrals. And there are some situations where computing volume integral is far simpler than the surface integrals. So on my left side, the flux is a double integrals of vector field F over the surface S, and towards my right side is a triple integrals of divergence of vector field F over E with respect to dV. And point number 2, sometimes divergence of F is much simpler to work with than the vector field F itself. Okay, so now let's start solving the problem using divergence theorem. Let me scroll down. That's better. So first example 1, use the divergence theorem to set up and evaluate the integral for the net flux of vector field, where vector field is given as capital F equals to x cubed over 3, y cubed over 3, z cubed over 3 over the sphere, unity sphere, x square plus y square plus z square equals to 1. So first the formula. So the flux equals to the surface integrals of vector field F over surface S, and the divergence theorem converts the double integrals to the triple integrals. So the flux equals to triple integrals over E of divergence of vector field F dV. So let's compute divergence of vector field F. So the divergence of vector field F equals to, this is the nabla operator, dot, this is the vector field F given. So you take a dot product and it gives you x square plus y square plus z square. And now our surface is sphere, so let's use a spherical coordinate to find the limit for our triple integrals. Let me scroll down. So using spherical coordinate, x square plus y square plus z square becomes rho square, and the volume element dV becomes rho square sine phi d rho d phi d theta. And in this sphere, rho, our sphere is a unity sphere, so rho lies between 0 and 1, phi lies between 0 and pi, So 0 is the north pole, phi is the, pi is the south pole, theta is just a 0 to 2 pi. Then the flux equals to the triple integrals of divergence of f, which is simply x square plus y square plus z square is rho square, and then dv is rho square sine phi d rho d phi d theta, and in d rho d phi d theta order, rho integral is our inner integral whose limits are 0 to 1, phi is our middle integral whose limits are 0 to pi, and theta is our outer integral whose limits are 0 to 2 pi. Great. This is the setup for the flux using divergence theorem. Let me scroll down. Next, let's evaluate. So we can evaluate this integral separately. So theta integrals, phi integrals, rho integrals. So theta integral gives us 2 pi. Phi integrals, the integration of sine phi becomes negative cosine phi. Put phi value 0 to pi. From the rho integrals, rho to the power 4 becomes rho to the power 5 over 5. Put rho equals to 0 to 1. Then put the upper limit and lower limit and simplify. So this gives us 4 pi over 5. Great. So in example 1, we compute the net flux of given vector field over the unit sphere using divergence theorem, which is 4 pi over 5. Great. Now let's move on. Example 2. Let S be a unit cube. One corner is at the origin and one corner is at the point P11, so that all its edges are parallel to one of the coordinate axes. Then, let me scroll down, compute the flux of vector field F. So I sketch the cube here. So the point P is 1 on 1. So all the edges are parallel to the coordinate axis. Then our vector field is x, y, z, computes the divergence of F, which is 3. Limit are x between 0 and 1, y between 0 and 1, z between 0 and 1. Then the flux equals to the triple integrals over E of divergence of F dv. And this equals to divergence of F is 3, z integrals, y integrals, x integrals. With respect to dv is dz, dy, sorry, that should be dx. It's a typo there. And the integrand function is constant, so we simply multiply by the upper limit. So 1 times 1 times 1 times 3, which is 3. So we found the flux of the unit cube. So this example is a good example to show computing the surface integral is way harder than computing the volume integral, or computing volume integral is way simpler than computing the surface integrals. Great, let's move on. Now example 3, that's better. Example 3 says calculate the surface integrals, double integrals of f over s. That's the surface integral of f over s, where given vector field is 3xy square, x is z, z cube, and s is the surface of solid bounded by the cylinder, y square plus z square equals to 1, and the planes x equals to -1, x equals to 2. So the surface is here. So this is the cylinder, and the plane x equals to -1, this one, x equals to 2, this one. So the formula, so the flux equals to surface integral of vector field f over s equals to the triple integrals of divergence of vector field f over the region E. This region E is bounded by the surface S, and triple integral is with respect to dv. Now this is a cylinder, so let's use the cylindrical coordinates to compute the limit of our triple integral. So then dv is in cylindrical coordinate r times dz times dr times d theta. Great. So let's start. First compute the divergence of vector field f. So our vector field f is given here. So compute the divergence here. Divergence is of f means nabla dot f. Then this computation gives us 3 times y square plus z square. Then use a cylindrical coordinate, put y equals to r cosine theta, put z equals to r sin theta, use square and add them, y square plus z square equals to r square, we can put this one later here, and x is x itself. Now let's find the bounds for the integral. So x between -1 and 2, -1 and 2, -1 and 2, and then for yz converted to the polar form or the cylindrical, then theta between 0 and 2 pi, and r between 0 and 1, because this is a circle in yz plane. Great. And also dv equals to r times dx times dr times d theta. Awesome. Now let's move on. Oops. That's better. Yep. So hence the flux equals to the triple integrals of the divergence of vector field f. We found divergence of f is 3 times y square plus z square. So in cylindrical coordinate, y square plus z square becomes r square, so 3r square, and dv becomes r dx dr d theta. So in dx dr d theta, our x integral is our inner integral, whose limits are -1 to 2. R integral is our middle integral, whose limits are 0 to 1. And theta integral is our outer integrals, whose limits are 0 to 2 pi. Then let's integrate. We can integrate separately. So 3 is constant, pull outside. And from d theta, the theta integral gives us 2 pi. And then the r integrals, r square times r is r cubed. Integration with respect to dr is r to the power 4 over 4. Put r limits r equals 0 to 1. And dx, the integration of dx becomes x, limit r -1 to 2. Then put r equals to upper limit, put x equals to upper limit minus lower limit, and simplify. This gives us 9/2 times pi. Great. So this ends these sections. So in the next class, we'll cover the Stokes theorem. Thank you.